Well, hello. Here we are again. I can't see any questions in the chat. Are there any questions? Okay. If there are no questions, I would now try to talk a little bit about important quantities that we use macroscopically. I mean, if you go to a shop in Prague, could be, for example, GM Electronics, Russell, or other shops for radio amateurs, you would want to buy a resistor. A resistor is a tiny thing having two terminals, and in fact creating electric circuits. You are not interested very much at what is inside a resistor. You have something which has got two terminals. It is called resistor. Well, and you are interested in the current and voltage over the resistor, and the ratio is what is important. So you could express that like voltage is equivalent to resistance multiplied by current, or the current is conductance times voltage. That is R is 1 over G. But anyway, you are not very interested in what happens inside, provided that this simple circuit element keeps the ratio between current and voltage. Now we will, in the electromagnetic field theory, investigate the situation a little bit from inside, with the aim to get one simple value for a thing that is a bit complex. And we will do that using an experiment or thinking about a disk. Let's have a disk which is one layer cut out of a cylinder, and that disk has some dimensions. So to draw it, we would have a circular shape with the radius A, and this shape, if we watch it, so this shape would look like this, and it has some thickness. We will denote it C. Now this disk is very nice, just very simple. To make it a little bit more complicated, we will drill a hole in the center of that disk. So we have a hole here with the diameter of B. Well, B is less than A, otherwise we would be left with no remains of the disk. So now we can see that we have a disk with a hole inside. And now we will turn it into a resistor. And we will do that in three ways. So how to turn this disk to a resistor? Well, for example, we would use vacuum deposition. Let's say that the disk is from some conductor but not a perfect conductor. For example, it is a piece of carbon. Now we can put the disk into a vacuum chamber, heat it a little bit so that it is hot. Then we can evacuate the chamber, wait a little bit so that the disk loses all the gas which is inside the disk. after some time we can put there a very hot gas, for example out of some metal, for example silver, and it would sit on the disk, and we can in that way create two electrodes, one upstairs, one downstairs, so we would have the disk contacted in the way that there would be one contact and the second contact. We would have somehow to cover the inner hole and the outer surface so that there is no silver. So we have only silver here and here, and we have two electrodes that are inside, and those electrodes are providing current into that disk. So we have feeding electrodes, and our question would be, okay, what would the resistance or conductance of that object be? So how to find it? Well, first we should think about the nature, about the shape of the field that would be there. Those two metallic electrodes, upstairs and downstairs, would create equipotentials. They are much more conductive than the rest, so there would be no tangential field, because if it have somehow happened, it would exactly at that moment drag charges, and those charges would move as long as they would cancel the field. So metallic surface is an equipotential, and we do not have to bother with tangential field components there. Now we have something which would create now a homogeneous field where the current would flow from upstairs to downstairs, and this is the plus and minus pole of the feeding voltage or current. So now we have a homogeneous field where at any point the flux would be of the same density. This is possible because the surface of both electrodes is the same, and the profile of the conducting path does not vary with distance. So we would have a homogeneous field. At any point of that field, we would have the condition for Ohm's law in differential form satisfied. So we have, at any point of that resistor, we would have current density which is proportional to the field strength, and the constant of proportionality is the specific conductivity. Now, the electrodes are in a constant distance c, so that we would have the electric field strength E equivalent to a ratio between voltage and the thickness of the disk C. So we would have E I would stop using vector notation now. E would be B divided by C. But at any point of this, we could now draw the current density. J is then equivalent to conductivity multiplied by voltage divided by thickness. And now, how much current do we have in this conductor altogether? Well, we can, for example, put here a cross-section line and count all the current flowing through. If the line is perpendicular to current lines, we do not need to bother with dot product in the integral. So we again remember that the current is an integral over current density multiplied by the element of the surface in a dot product. But as those two vectors are collinear, we can forget of dot products, just use magnitudes. And after all, because the current density is constant, this integral reduces to a product of the surface and current density. Now, how big the surface is? Well, it is the surface of this circle minus the surface of the circle that has been drilled off. So the surface of a circle is pi r squared. So that's pi a squared minus pi b squared. That's the surface, the cross-section through which the current flows. And now I can put an equation for that current. It would be current density times surface, so that the total current I is pi minus b squared plus a squared I continue here with the current density, which is sigma b over c. So now I have to dress it better. Now we have I is equivalent to pi minus b squared plus a squared multiplied by v and sigma and divided by c. So this is our equation for current and voltage. Now if we compare it to this equation, current is equivalent to conductance times voltage. We have the equation just here. We can get current, we have voltage, and the rest of the equation must be conductance. And we can then easily get it out. So we have established a constant of proportionality between current and voltage. For this case, we have started from inside. We have been examining the electromagnetic field, that is the steady current field now, and we have arrived to an equation of proportionality between current and voltage at the outer terminals. So now we can manufacture resistors, and by varying the material properties, that is the conductivity, the specific conductivity, by varying those two diameters and the thickness or the length of the resistor, we are able to produce resistors or conductors of different conductance, and therefore we would be able to provide radio amateurs with different resistors. Well, nice. You possibly think, why has he drilled the hole inside? That's uneasy, and it does not change the behavior of the resistor very much. It only makes the equation more complicated. Well, okay, this is because I want to use the same shape in a different manner later. So now please, the important points. we have established a resistor in a manner that geometrically creates a homogeneous steady current field inside it. So at any point we have the same field strength E and flux density, that is current density, J. The direction does not change, the density nor the strength changes. So this is called a homogeneous field. And within this field, we just can easily get the value of the integral value, that is current here, by multiplying current density and cross-section. Now I will use a different way for the same geometry where the current field would not be homogeneous, and therefore we would have to use another kind of computation, a real integral computation. So let's take the same surface, just we would immerse that resistor into, for example, strong acid and get away all the metal out of it. So we will be left only with a carbon disc with a hole inside. And now we shall again deposit conductor on it, but not on those two surfaces, but only inside the hole and on the outside of the disc. So now the current would have to flow this way or this way. So that's a difference. The second case would be such that we will have a current flowing this way, radially, from the center to outside. So we will have one contact here and the other here. And in order to establish the value of this resistor, we would have to use integral calculus. In fact, this is why integral calculus has been invented. I have to tell you that the most used trick, that is, we will have average cross-section somewhere here and use average field strength, will not work. I took average field strength. Well, okay, because there is smaller surface here and bigger surface here, the current density depends on the radius, on the distance from the center of the disk, and therefore you have more dense field here than here. Also, the field flux lines are not collinear. So this field is not homogeneous anymore, and we will have to make an exact calculation to find out the value. How to do that? Well, let's think of a small element of the disk that guides the current. Now let's cut the disk like a piece of onion. You know, an onion, if you cut it, is composed of many layers. But if you take one small piece of that onion, you could strip very thin layers from it. And this is a thing we would do. So let's say we have a very thin layer. And this thin layer has some thickness. As it is very thin, we call it dr. Now please, could you read the red pencil?
Yes.
Well then, I prefer to have two colors at least. So we have the differential thickness of this thin layer, dr. Of course, it has, the layer has some radius r. Now we have the current flowing from the inner conductor to the outer conductor through a set of layers. In fact, it first passes the first layer inside, then it passes the second layer, then it passes the third layer, then it passes our layer, and then it passes other layers up to the outer radius and conductor. So in fact, what we have here is a set of tiny differential resistors that are connected into series. The current is flowing first through the first resistor, then through the second, then through the third, and this is called, in the circuit theory, connection in series. And connecting resistors in series means that the total value for the whole chain of resistors is given as an algebraic sum of those resistor values. So you can add those resistors to get an integral value. Now we would do the same, but we should first establish the value of this very tiny resistor, and then we will be able to add it. So we need a new sheet of paper. For resistors, it holds that in a homogeneous field, the resistor R is equivalent to the length of the resistor divided by the surface of the resistor and divided by conductivity of the material. This is the equation that sets up resistor value in the case that you have a homogeneous field. Length, the longer the resistor is, the bigger the value is. Cross-section, inversely proportional, and specific conductivity. Now, this holds for homogeneous field. We could not use it for the field in the disk because the field is not homogeneous. But the trick of integral calculus is that we take a very small element where those two radii differ only by a differential piece, and the differential piece is as a limit process of no thickness, so that the value of current density here and here is the same, and also the field strength is the same within this small differential, let's say, onion skin layer. And therefore, we can find out the value of this differential resistor because it's so tiny that the field within it is homogeneous. What would be the resistivity, the resistance of only this small layer? Well, we can follow this equation so that we would have dr, that's the value of the differential piece of that resistor. It would of course be inversely proportional to the specific conductivity of the material. And now there is the length and the surface. Well, the length, okay, the length of the current path through this resistor is dr. It just flows radially out. What is the surface? Well, that's the cylinder which runs at the radius r, and it has the height of c. So it must be c multiplied by 2 pi r. So the cross section is c over 2 pi r, sorry, c times 2 pi r. and the length is dr. Now distinguish, we have on the left side a differential of the resistivity, the resistance, sorry, which is big R, and this is the diameter small r. Well, so we have the differential, now we have to get the integral value. Well, that's simple, we just integrate. So the r would be the integral from, well, the inner radius is b, the outer radius is a, the current flows from inner radius to outer radius, and what do we have inside? Well, we have there dr over sigma c 2pr. Well, this is quite simple because this, and this are constants. So in fact, we can get all those constants out of the integration process, and we have only a kind of integral of dr over r, which is a simple textbook integral, and the result would be and that's it. So now we have an equation establishing the value of the resistor, but we have considered the inhomogeneous field. So we have an equation which exactly describes the resistivity or the conductivity, dimensions, and its attitude to the value of the resistor. Again, this calculation is based on the most important trick that gave birth to integral calculus. If we have inhomogeneous field, we can still get the result using integral calculus, provided that we can find a small element that is so small that the field inside could be treated as homogeneous. And we can somehow change those elements to get the total value. That is, to add them or to integrate. For resistivity, we did it in this manner. Your questions, please. So far, no more questions. So let's train this once more with the same disk. So let's consider again that we get our old disk. We put it again into some acid and get rid of all the metal deposited on the surface of our carbon disk. Well, in order to have another way of exploitation, we would need a very thin saw, and we would now cut the disk with a very thin cut, so that now we have interrupted the disk. We have a kind of C, but with a very thin dividing layer here. And we got the metal, well, I will magnify it a little bit, so we have very thin but non-conductive cut here, with one metallic layer here and the other metallic layer contact here. So now we will have again a resistor, But instead of having the current flowing from inside to outside, the current would run around the disk. But as you can see, the path in the middle, in the center, is quite short when compared to the path at the outer side. So that we can expect that the current density inside would be much bigger than the current density here. And at the same time, the field strength just here would be much bigger than the field strength outside. And therefore, we will have to handle an inhomogeneous field again. So how to do that? We can use again integral calculus. We should use integral calculus, but we can use the same shape of the element as the current lines would be concentric circles here due to symmetry. So we can cut out one concentric cylinder, one onion skin layer, and the current runs around the circle here through that layer. But now dimensions have somehow interchanged. First, this is the length of the differential path, and this multiplied by the depth is the cross section. So again, we now can put down an equation for the differential resistor value of this thin skin. We will start from the same basic equation, but as those values, the same letters have now different meaning, the length is 2 pi r, while the surface is dr multiplied by c. So now I will get here a similar equation for the second case. We have dr equivalent to 1 over sigma, specific conductivity, and now multiplied by 2 pi r and divided by drc. Now, there is a second important point we have to discuss. In our first inhomogeneous case, the current was flowing in this direction so that those differential resistors have been connected into series. But now we have established an element in which the current flows and does not interact with the other current in another layer. So in fact this is not connected in series, but all those current paths are connected parallel to the metallic electrodes. So now we have a set of resistors, differential resistors, that are connected in parallel. But as you know, when connecting resistors in parallel, you can't simply add their values. What you add is not resistor values, but conductance values. So okay, let's upgrade it this way. dg is, well, sigma c dr over 2 pi r. That's just dividing 1 by the first formula. So we have now value that could be added when connecting those layers in parallel. And we can again get the total value of conductance. So we have G as an integral of this differential value. We will again integrate from B to A, and inside the integral we would have sigma c dr over 2 pi r. Again, this integrand is mostly composed of constants. This, and this are constants. We can get them out, and we have the same kind of integral dr over r. So now I will put down the result as sigma c over 2 pi logarithm a over b.